Hi, hi, everybody. Welcome to 1.11 scales of notation. This is another word for what we call bases. Basically, if M and N, that's Mike and November, M and N, are positive integers where N is greater than 1, then M can be represented in terms of N in one and only one way. That's important. That's significant. In the form m is equal to a naught times n to the h plus a1 times n to the h minus 1 dot 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 plus a sub h minus 1 n plus ah. Notice that so in other words, m can be written as a linear combination of powers of n. That's really what's going on over here. And so a naught doesn't equal 0. So you want the first one, at least the first one has, at least the first coefficient has to be non-zero. All the other coefficients are between 0 and n, less than n, and the I is, I guess, what's the index. Anyway, now this could be, why is this possible? Well, you do the division algorithm basically, because uh, m is equal to n naught n plus ah with these restrictions on the side. N naught and then is equal to n1 n. N1 is equal to n2 n plus h2. Da da da. It keeps on going down, 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 and we just basically keep on using the division algorithm over and over. It's not quite the same as Euclidean algorithm. It's the division algorithm used multiple times. Until we finally get all the way down to the bottom where n sub h minus 1 equals a naught. That's the last state. There's no more n's anymore. Now this is going to end eventually because these numbers are getting smaller and smaller, and they're less than some finite number n, so they are going to get down to a bottom. And the value of the last now, if the value of the last of the n sub h minus 1 from the last equation is substituted into the second to last. So I take this here and I plug it in over here. I get n sub h minus 2 equals a naught n plus a1. And then I could continue substituting in a similar manner. N sub h minus 3 equals a naught times n squared plus a1n plus a2. And I keep on substituting, I keep on back substituting over and over again. Eventually, what I'm going to wind up with is m is equal to a naught n to the h, a1 n to the h minus, I'm going to wind up with this thing. And this is really kind of the same thing as writing a number in a different base. Let's see, to prove that. Now, how do you know this is unique? Well, it's unique because we said one and only one. We know it's unique because if I would have another representation, suppose m was also with the b naught n to the k, b1 n to the k, and so on, dot, 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 and of course the first b naught does not equal 0, and so on and so forth. If I just set these two guys equal to each other and bring all the n's over to one side, I get on the left side here, everything is divisible by n. So this is a multiple of n. On the right side, this has to also be a multiple of n. But since bk and ah are both less than n, the only way that their difference could be a multiple of n is if the difference is 0, which means bk equals ah. So that equals 0. Once that equals 0, and then I continue setting everything equal to each other over and over and over again, and I'm going to wind up with basically everything being the same. We've had this sort of argument before. Now here's an example where if I have the number, this is in base 10, 1, 2, that would be 120,759. That's equal to 1 times 7 to the 6th power, plus 1 times 7 to the 4th, plus 2 times 7 to the 3rd, plus 3 times 7, plus 2. Notice that all the coefficients are less than or equal to 7, or less than, I'm sorry, less than 7, less than 7. Another way of writing that is that 120,759 base 10 is equal to 101,101,2032 base 7. And this is really what we would call bases, writing numbers in different bases. The only, now, there's a very cool case. What if n is equal to 2? Well, if n is equal to 2, that's going to give us the very famous thing called binary. Any positive integer can be represented in one and only one way, as a sum of different powers of 2, and that's called base 2 or binary. And that is all I wanted to show you for now on this. Um, I just want to show you just in a more, whatever, less fancy way. So you want, if you have the number 3, 4, 5, 6 base 10, and you want to convert it to base 3, or that's what scales of notation means. Well, the powers of 3 are 1, 3, 9, 27, 81, 243, 729, 2187, 65, 61, and that's as far as I go, because once I go up to but not exceeding 3, 4, 5, 6. So the last one here, of course, the last one on the list, the highest power that doesn't exceed is 287, 2187. I'm sorry. Now 356, 3456 equals 1 times 2187 plus 620, 1269. 1269 is equal to 1 times 729. I'm going down now. I'm just going down the powers of 3 plus 540. 540 equals 2 times 243 plus 54. 54 is equal to 0 times 81, and 54 is also equal to 2 times 27 plus 0, 0, 0, 0. So so this comes out, this means in totality that 33,456 base 10 is equal to 112020000 base 3. And that is an example of how this stuff works. Of course, in binary, it's even cooler. And you guys, a lot of you guys, I'm sure, are computer majors or CS majors, whatever you call yourselves. And I'm sure you know a lot of stuff about computers. Okay, well, that's the end of this video. It's been lovely, and we will see you guys next time. Bye, everybody.